quiz 4. And the plan for today is very simple. So I want to say a few words about this, but then we'll be doing section 6.2. This is the section about average value. And then if we have time, we'll begin section 6.4. Because for this section, we have actually 2 classes. So if we have time, we'll begin this one. If not, then we'll do next time. Okay, so let me do one example. One example of this kind of definite integral when it's from negative to positive infinity, very quickly. So here's this example. Let's say that we want to compute this area, which is enclosed by the function y equals y1 divided by this polynomial. It's a rational function. And let's say we want to compute this definite integral, but improper. And I want to evaluate this from negative infinity all the way up to positive infinity of this function f. And the function is the rational function 1 divided by 1 plus x squared. 1 plus x squared. When you know, we did this example the other day, but the thing is that there was office hours and maybe some people couldn't be with us. So that's, I want to say a few words, just 1 second about this example today. Okay, so what we do is we split this integration into 2. Then first we go from negative infinity up to 0. So first we go from negative infinity up to 0 of the same function. Function is the same, 1 divided by 1 plus x squared dx. And then we go from 0 all the way up to positive infinity. So then we go integral from 0 to positive infinity. And the function is again the same, 1 divided by 1 plus x squared dx. Okay, this is an improper integral because the limit of integration is infinite, and so is the other one. There are 2 improper integrals, and so we evaluate them using the idea of limit. So let's do one at a time. Let's do this one first. How to compute this integral from negative infinity to 0? What I'm going to do is I'm going to fix some point, maybe in here, and I will be looking at this integral from this point up to 0. So this is really this area. This is this area. So I'll take the integral. I don't know, I'll call this point t, for example, or some other letter, but maybe t, and I'll integrate from t all the way up to 0 of this function. So 1 divided by 1 plus x squared dx. And what this definite integral is, that's exactly this area from t to 0. But what I want to do is I want to go with this point t all the way up to negative infinity. So I'll compute the limit of this when t goes to negative infinity. When t goes to negative infinity. And that's exactly the first integral. Now let's do the other one, and we'll do exactly in the same way. So what I have to do is I have to fix some point t, or maybe parameter t, that's bigger than 0. And then I will integrate this function from 0 up to t. So I'll be looking at this area. So from 0 up to t of this function, 1 divided by 1 plus x squared dx. And I want to compute, again, I want to take and see what's happening when this parameter, this area, goes to positive infinity. So I compute the limit of this when t is approaching positive infinity. So this is exactly the other integral. So plus this one. This is the first one, this is the second one, and now we have to evaluate one at a time. So this is equal to This is equal to that. Let's continue this. Now I will be evaluating this definite integral using the fundamental theorem of calculus. When I do so, I'll compute the limit of this. And notice that this is going to be a function of t. So let's see. I want to find one antiderivative of this function, 1 divided by 1 plus x squared. That's the function inverse tangent. Tangent inverse of x. And I want to indicate that I want to know what this function is equal to when x is equal to t, when x is equal to t, and then when x is equal to 0, and then compute the limit of this difference. Compute the limit of this when t goes to negative infinity. Then we'll do exactly the same thing with the other integral. So we have plus. The other integral is this one. Antiderivative of this function, again, this is tangent inverse. I'm using fundamental, and I want to know what this function is equal to at 0 and then at t. I want to know what this function is equal to when x is equal to 0, and then when x is equal to t. And then once we compute this number, it will depend on t. And then I'll take the limit of this expression when t goes to positive infinity. Okay, so now let's use, again, the fundamental theorem of calculus. What is this? This is tangent inverse of 0, tangent inverse of 0 minus tangent inverse of t. That's exactly this number. And then I have to take the limit of this when t goes to negative infinity, and then plus the same thing, limit t goes to positive infinity. This is tangent inverse of t, tangent inverse of t minus the inverse function tangent at 0. Okay, so I have to compute this and this. And now let's see what this limit is equal to, what this limit is equal to. Let's recall how the function tangent inverse looks like. So the function, this is the given function, y equals this one, that's the function given. And antiderivative of this function is the function tangent inverse. So let me sketch the function tangent inverse for you. So the function tangent inverse has two asymptotes vertical. One is at pi over 2, and this is one vertical asymptote of this function, and the other vertical asymptote of this function is at negative pi over 2. So at negative pi over 2, and here's another horizontal asymptote of this function, and the function itself, you know, it looks like this. So this will be like this, and then at 0 the function is 0, and then at pi over something like that. This function will be asymptotically approaching this line when t goes to positive infinity. So now let's look what's happening with this limit. Tangent inverse, that's the function tangent inverse. This is the function tangent inverse. And now this is a question I would like to ask you, because I want to see if my computer is working well and I have all the connection. Let me just admit those two people. Admitted. Okay, question for you is the following. This is the function tangent inverse at t. We are looking at this portion, tangent inverse at t, and I want to know what's happening with this function when t, the input, goes to negative infinity. So when the input of this function goes to negative infinity, the function itself is approaching what number? Perfect. The function is approaching negative pi over 2. This is perfect. So this is approaching negative pi over 2, and this is another negative. So I have negative and negative, so positive pi over 2. But of course, tangent inverse at 0, that's 0. So that's this. And then the other one is tangent inverse, the same question for you. Also, I want to ask you because I want to see that my computer is working well. So here's the function tangent inverse. And I want to know what's happening with this function when the input of this function is approaching positive infinity. This is the function. What is this function asymptotically approaching to when the input goes to positive infinity? Perfect. Yes, the function is approaching pi over 2. So this limit is pi over 2. Okay, but this is tangent inverse at 0, so that's 0. And this is 0 as well. So the first integral is pi over 2. And the second one is also pi over 2. And see, you can notice that this is really symmetric because we have computed this area pi over 2. It's this region from negative infinity up to 0. Up to 0. You know, and then you can tell just looking at the graph that this should be symmetric. And we have done this computation just to confirm what we have. This is just a picture to something to support our intuition on, and this is the formal computation. But indeed, this is pi over 2, the first region, so to say, and the second one is also pi over 2. So if you add those two numbers, okay, that's it. So this definite integral is convergent because this limit exists and this limit exists, and then so the answer to this question is this definite integral is convergent, and it does converge to this number pi, which is, I don't remember exactly, but approximately equal 3.1 and something else, maybe 4. It doesn't matter. This is the answer, pi. Okay, that's the end of this example. Let me admit those two people, this one person, admit. Okay, don't be late, people, please. So one example was this. The other one, very simple because we did this the other day. So this is the area between two functions. We won't be doing details because we did something like this in class, not in the office hours last time. So just want to mention, let's say, for example, I have those two, A1, A2, but say, for example, you want to compute A1. You want to compute this area, A1. So this area is enclosed by two functions, the first of which, or one of which, is the function cosine. And here's not the whole function, but a portion of this function cosine. And the function actually looks like this, and so on and so forth. And the other function is the function sine. And here's a portion of this function sine, and I want to compute this area A1. So the area A1 is going to be equal. Okay, first of all, we need to solve this equation. And the equation is very simple. We have on one hand side, we have the function sine. And on the other hand, we have the function cosine. And let's say we are considering x's between 0 and pi over 2 only. The question is for what value of x? But remember, x is supposed to be taken only from this range from 0 to pi over 4. And the question is, if this is the range of x, then for what value of x specifically those two functions are equal? But we know that this point is pi over 4, because at this point, those two functions are exactly equal. So now very simple, how do we compute this blue area? Very simple, we take the big function, which is cosine x, and then minus the small function, which is this function sine x. Okay, and then we evaluate this integral from 0 up to pi over 4. Okay, and then we know how to compute this. So take antiderivative of this function, and use fundamental theorem of calculus. That will give you the area. So I did this computation over here. So the area A1 was the function cosine minus the function excuse me, minus the function sign. And this is from x equals 0. So from this point up to x equals pi over 4. So up to this point. And what this definite integral, this exactly says that this is the blue area. So this one, A1. Okay, so antiderivative of cosine is sine. Antiderivative of sine is negative cosine, so negative, negative, positive. And then take this function and evaluate this function at 2 points. Namely, when x is equal to 0, that's this point. Then, of course, the other one when x is equal to pi over 4, that's this point. Okay, and so this is this minus that, and that will give you the answer. Okay. The same, we can do the same thing with A2. Area A2. Let's do just for practice what that would be. We won't be doing the computation, but that would be very simple because it would be integral from pi over 4. I'm looking at this area A2 now. So this area, this is the area of interest. And I want to know how to compute this area. Very simple because the integration will go from pi over 4 all the way up to what point? Pi over 2. And then, okay, question for you. What is the function in here that we will be integrating? First of all, we'll have what function minus what function?
Negative pi over 2.
Pi over 2.
Perfect. This is exactly the function that we will be integrating from pi over 4 to pi over 2. So let me just repeat what you just have said. So sine of x, sine x minus the function cosine, and we won't be doing this computation now. This is exactly the area. I have done this computation over here. So this is sine of x minus cosine x. When you do the computation, you get square root of 2 minus 1, and that's the area. And you can notice that it's exactly the same. Again, it's symmetric, so it's the same as that. Okay, so that's all what I have to say about the quiz. So we did one example of this definite integral from negative to positive infinity. We did one example of how to compute area between functions or between curves. Very nice area, very nice section. So please review very briefly those sections. Also, I put some suggested homework problems, so you're most welcome to look at. Some of them, they have solutions actually. So you can do by yourself, and then you can look at the solution. Okay, so now I want to do new section. What time is it? Perfect. So I want to do new section, which is average value of a function, 6.2. And then if we have time, we can begin this section, because for this section, we have a lot of time. We have 2 classes actually. So one thing at a time, let's do 6.2. Okay, 6.2 is the section average value of the function. Let me find this. Okay, here it is. Section 6.2 is about the average value of a function. First, what I want to do is I want to define what do we mean by the average value of a given function. And then I would like to give you the main result in this section, which is called the mean value theorem for integration. You might recall this is the mean value theorem for math 2b as well. But this one is not for differentiation, but for integration. So the main result in this section is the mean value theorem for integrals, not for derivatives, because we did for derivatives in math 2b and so on and so forth, or 2a, excuse me. This is for integrals. So first of all, let me define what do we mean by the average value of a function, and then I'll give you some intuition how to think of this. First of all, formal definition. And the definition is the following, very simple. So take a function, we'll be taking average value of a function. So let's say we have a function. Maybe the function is defined from some point A up to some point B. A, for example, could be 1, and B could be 17. Those A's and B's, those are just numbers, you know? And take a function f, I'll call this function f. Maybe the function looks like something like this, something like this. Okay, for example, that's my function f. That's my function f. This is my function f. Now the question is, okay, the function is defined on this interval from a to b. Let's try to analyze this function and see how this function, this specific one, how does it look like? Well, at a, the function is, this is the value of this function at a. Just one value. Another value of this function is at b, and this is the value, this point. So let me make this y-axis a little bit bigger. Okay, so this is another value of this function. This is another value of this function. This function has so many values in between, so many values in between. This is the minimum value, the minimum value. And on the other hand, this is the maximum value. And then this function has so many values in between, but like intuition is that somewhere in between should be the average value of this function. This is exactly the concept of average value function. That would be the average value, something in between the maximum and the minimum. That's just intuition and very informal, but let me give you the formal definition of what we mean, and it's right there. So I want to just recopy the whole thing. So by definition, so let's say definition. So the definition, let f be a function defined on some closed interval a, b. Then the average value of this function f, and that's a notation the textbook used, but I'll be using the same. Okay, so the average value of this function f defined on this closed interval a, b is the following number. So to compute the average value is what I'm going to do. It's going to be a fraction. Then on top, the numerator of this fraction is going to be very simple because it's going to be just the definite integral from a to b of this function f. This function f. Okay, and then I'm going to divide this number by the length of the domain of this function f, which is simply b minus a. That's the length of this domain of this function, which is b minus a. Okay, that's all. This is the formal definition. That's what they mean by the average value of a function f defined on some closed interval ab. Okay, that's the formal definition, but how to think of this? We can think of this, you know, in the following way. So think of this, you have some function f defined on some closed interval from a to b. And let's say maybe the function, you know, that's just one example, but it's a function, it's an example, we can kind of support our intuition of how to think of the average value. So when you have a function, then let's say the function has somewhere minimum value, but also on the other extreme, excuse me, on the other extreme, the function has maximum value. So this is max of this function, but somewhere in between is what is a point that's called the average value of the function, and this is the number f average. Average value of a function is a number. And how do we compute this number? Very simple. All I have to do is I have to look at this fraction, and on top of the numerator is simply definite integral from a to b of this function. So this is the area, and then divided by b minus a. So divided by the length of the domain of this function. So this is definition. And now let me give you the main and the most important result of this section, which is the following. The main result is the theorem which is called the mean value theorem for integrals. And this theorem says the following: if the function f is continuous, if the function f is a continuous function and is defined on some closed interval from a to b, then there exists a point C in between A and B. So a point C in between A and B, such that so the point, the point C in this example would be right here. This is the point C would be right here, such that if you compute the value of this function f, if you evaluate this function f at this point C, that will give you exactly the average value of this function. It's a beautiful theorem, and we'll say why this is significant in 1 second. Then f of c would be equal to f average. So it might be, maybe at this point we don't see why this might be useful, but in a second we'll see. The average value of this function will help me very much. So if I know the average value of this function, I can compute the definite integral. The point of the average value of this is to compute the definite integral. Why this is so? Let me just say in 1 second. Okay, so this is essentially that's all what I have to say in this section. In this section, we have one definition. And the definition is that the average value of a function is defined in this simple way. So that's the definite integral divided by the length of the domain. This is the definition. And the main result of this function is it is applicable not for all functions, but only for those that are continuous. I could give you, we have no time, but I could give you an example of a discontinuous function where this is not true. Well, but we have stated this, that we need continuity of this function f. Again, if the function f is continuous, then you can find a point C. Here it is. You can find a point C in the domain of this function as a point in between A and B, such that if you evaluate this function f at this point C, that will give you exactly the average value of this function. Why this is important is because this will help you sometimes compute the definite integral. So let me give you now, that's all what this section is all about. I want to just mention a couple of examples. Excuse me. Okay, here's an example. And let's see. Oops, where is it? Okay, take a function f. So let's say my function f of x, very simple function, 1/2 x. Okay, here's the graph of this function. And let's consider this function not for all values of x, because to specify average value of the function, I have to specify not only the function, but also the domain. So let's compute average value of this function, but only for x's between 0, so 0 and 20. For example, I'll take only those x's. 0 and 20. Okay, so here's how this function looks like. Here's how this function looks. This is 0, this is 20, and we'll compute this average value of this function in 1 second. We'll compute because we have formal definition. But before we compute the average value, let me ask you this question. What would be the intuition of, what is the intuition of the average value? What the average value should be equal to? So let's see. Okay, this is the minimum value of this function. Okay, and then This is the maximum value of this function. This is max. This is max of this function, and it's 10. So the function takes so many values between 0, there's one value, there's so many values between 0 and 10. And what would be the intuition? What would be the average value between 0 and 10? The intuition will be that would be 5. And when we do the computation, then we should get that this is f. Okay, I don't know how to write this, but this is the f average. F average should be equal to just, this is the intuition, should be equal to 5. So let's compute the average value of this function, but formally, f average of this function is equal to, how do we compute average value of the function? In a very simple way. All I have to do, I have to take this function f and evaluate this from 0. I mean, not evaluate, but integrate from 0 up to 20. Up to 20 of this function f. But my function f is very simple function. It's 1/2 times x dx. And what do I have to divide this number by? By the length of the domain of this function, which is, what is the length of domain of this function? Perfect. The domain of this function is 20. Okay, so this is very simple integral. We won't be doing this, but when you compute this number, that will give you 5. That will give you 5, and this is exactly the average value of the function. Okay, so this is the average value of the function. And what does, okay, this is the average value of this function. So we know that, okay, so I want to say a few words about the mean value theorem. What would be the point C in this example? The point C will be equal to 10. See, you can tell just looking at this picture that there exists, this is horrible. There exists a point C, so I don't want to write other thing because this doesn't work well, but there exists a point C in between 0 and 20, such that if you compute f of c, this is equal to the average value of this function, which is 5. Okay, what is the point C in my example? This one. This is the point C. This is the point C. Okay, so let me say 1 second why this might be useful for computing definite integrals. See, on one hand side, if you look at this triangle, this one. Look at this triangle. What is this triangle? This triangle is the integral from 0 to 20 of the function f, which is 1/2 x dx. This is exactly this triangle. Okay, this is exactly this triangle. On the other hand, we have this rectangle. This is this rectangle. Here is another very beautiful, oops. Here's another rectangle. And the mean value theorem says that, okay, if you know the average value, then the area of this rectangle, this is something, but then on the other hand, you have this rectangle. And the mean value theorem says exactly this. If you know the average value of this function, then you can find the rectangle such that the area of this is exactly the same as the area of this rectangle. That's the key point of the mean value theorem. That's what this point C will tell you what is the height of this rectangle, because the base is just b minus a. the base we'll know anyway, but the point is to find an appropriate height so that the area of this rectangle is exactly the same as the area of this definite integral. And this height of this rectangle is exactly the average value of this function. Average value of this function. That's the height of this rectangle. And that's the point of, because sometimes this might be difficult to compute because it's a definite integral. But once you know the average value function, this is just simply computing area of rectangle, which is very simple. Base times height. And the height is exactly average value. The height is exactly the average value of this function f. You know, that's just one example, but let me do another. So those here are all the details. Another example, take this function f of x equals x, f of x equals x. So we have time. I was looking at time and we have time. So, and let's consider this function for x's between 0 up to 10. So take x's between 0, x's between 0 and 10. Okay, let's compute the average value of this function. The average value of this function f is going to be equal, very simple, because this is simply definite integral from 0 all the way up to 10 of this function x dx. Okay, and what do I have to divide this number by? I have to divide this number by the length of the domain, which is 10 minus 0, which is 10. Okay, so then you can compute this, and you will find, I'm not doing this computation now, but I'm looking at this geometrically. It's 5. This is the average value. This is the minimum value. This is the maximum value. And this is the average value. The average value is, the intuition is that the average value is something in between. Well, this is a very simple function, I know, so we can tell. But when the function is more complicated, like for example, x squared. So the function is f of x equals x squared, and consider not excuse me, consider not x's, but x's only between 0 and 3. Then if I want to compute average value of this function, then this is going to be equal integral from 0 up to, so this is 1, 2, 3, from 0 up to 3 of this function x squared. And then divide this by the length of the domain of this function, which is, what is the length? It's 1, 2, 3. Okay, divided by 3. Okay, so use fundamental theorem of calculus to evaluate this. So this is x cubed divided by 3. This is antiderivative of this function. And then evaluate this at x equals 0, and then at x equals 3, divided by 3. So we have 3 cubed divided by 3 minus, well, 0 cubed, well, that's 0, but I just want to write this down. 0 cubed divided by 3. This is the, and then divided by 3. Okay, and then when you compute this number, that will give you the average value. And I'm looking at the picture, and it should be, you can check, I haven't done that, but it should be about 3. Okay, so we have about maybe 5 minutes. So another example. Oh, this is the last example. See, let me just come back to this example for 1 second. On one hand side, we have this definite integral of this function x squared dx from 0 up to 3. So this is exactly the area of something that looks like this. So this is exactly this area. So it's difficult to compute this area, but once you know what is the average value of this function, the height of this would be, you can find a rectangle. In this example, that's a square, but in general, you can find a rectangle. So this is exactly the same. That's why you need to know the height of this, and the height of this rectangle is exactly the average value of this function f. So this is simple to evaluate, that this is not. Last example I want to mention today is this one. So again, average value function is this one. This is average value of a function. I have to specify not only the function itself, but also the range or the domain I'll be considering this function over. Let's say from 0 to pi over 6. So here's 0 and here's pi over 6. And the function x divided by 2 plus cosine the function looks like this. So compute the average value of this function. What we do is we take this integral from 0 to 6 of this function, and then we divide this number by the length of the domain of this function. So the length of the domain of this function is from 0 to 6 pi, so it's 6 pi. And then use the fundamental FTC. Use FTC to evaluate this definite integral. That will give you 9 pi squared. And then divided by 6 pi, which is the length of the domain, that will give you, this is the average value of this function. And what this is very useful information, because how we can use this information? Well, see, if you want to compute this area, no, okay, so it's not good, but if you want to compute this area, then you can find a rectangle so that this area of interest would be exactly the same as the area of this nice rectangle, and the height of this rectangle is exactly the average value of this function. This is 3 pi divided by 2. I have no calculator now. I could approximate this number, and I can see that something, maybe, let's see, this is 2, 4, 6, 8. So 2, 4, it looks to me like a little bit more than 4. But okay, we can check later. In any case, the area of this purple rectangle is exactly the same as the area of this wavy region. And that's the point of the mean value theorem. The point of mean value theorem is I have this integral from 0 to 6 pi, of the function f. Well, that's a function f, but f of x dx, and then divide this by 6 pi, and that's equal to the average value, which is 3 pi divided by 2. So if you multiply both sides by 6 pi, you get that the integral from 0 to 6 pi f of x dx is equal to 3 pi divided by 2 times 6 pi. But what is this? This is exactly area of rectangle. The base of this rectangle is 6 pi, so it's this. And the height of this rectangle is 3 pi by 2. So the area of this rectangle now is exactly the same as the area of the other thing. So in other words, you have this thing that looks like this, and you can find a rectangle, the area of which is exactly, area-wise, is exactly the same as this. This is the key point of the mean value theorem. So, okay, almost time. If you just give me 1 second, please, I want to say a few words about, just 1 second, few words about this section 6.4. Absolutely don't worry about this section now because we'll do this on next time.